data may live on some data manifold of lower dimension, but this lower dimension doesn't mean low dimensional. So those manifolds are still reasonably high dimension. So you also know that it's important, and this is where, in fact, most of the progress is, in fact, expected from AI models, is how to make our lives better, how to look after ourselves, how to take advantage of the availability of data and technology to increase our longevity, the quality of life. So medical data is another example, unfortunately, where the data is super high dimensional. If you look at a typical patient record, I don't know if many of you know this fact, but in fact it can be as high as 800 whatever dimensional, because it collects all the data that you have from, at least for a patient, all the history, all the analysis, all the different modalities. So these are rich and high dimensional data. All right. Now, what can go wrong? And this is the first thing. So the first 3 parts of today's lecture will be about what may go wrong. And the list is not exhaustive, and it's just examples, right? The examples of of things you need to look after. And the last part will be about how can you exploit high dimensionality to make things right? So therefore, please don't fall asleep. Don't fall asleep. So try to stay awake until the last part of my talk. This is where you will learn. Or maybe if you want to fall asleep now. And so sleep for about 1 hour and then wake up after 1 hour. Okay, good. And here is my favorite example as an illustration of issues around high dimensional data. So you know that high dimensional geometry offers you lots of examples to illustrate the phenomena. And one of the things is the so-called volume concentration. So we know that, let's say, if you take an N ball in high dimension and you fix its size to, let's say, radius 1, right? Then the volume is, let's say, some constant, and then we can normalize. We can take the volume and divide by the volume. But then if you look at the ratios of volumes of balls whose radius is r, and r is a number from 0 to 1, then what you'll have is that you'll have this picture. So you'll see that the ratio of the volumes of a ball whose size is r in n dimensions to the volume of a ball whose size is n is r to n, and r is a number from 0 to 1. And you see that when n is large, right, and when r is small, there is nothing here. So the ratio is negligible, and in fact you see that the behavior is exponential. So what this picture illustrates, and it's one of the easiest way to see what I'm going to talk about next, is that in high dimension, for example, for this if you were to sample points from the equidistribution in a unit ball, all the distances concentrate, all the points concentrate near the outer shell of the ball, meaning that all the distances become nearly identical, right? Nearly the same. So, and this is what I try to formally state in this fact for you, just to fix my point. So, in high dimensions, as I said, at least for these examples, for this distribution, for an equidistribution in a unit ball, distances somehow concentrate. So points concentrate near the outer shell, near the outer shell of the ball, meaning that the distances concentrate. But interestingly, yeah, and this is just an illustration of how can you do this. Not only they concentrate near the shell, there are some other effects, but let me just go to the next point. So if you think that this happens only for unit balls, then you're wrong, because it doesn't work this way. And unfortunately, if you take a typical scenario where you have, let's say, many attributes, and you believe that they're all independent and possibly, let's say, for simplicity, sampled from the same distribution, then in those instances, distances concentrate too. And one of these classical results is what I put here. So if you take an LP distance, let's start from the beginning. So you have a vector whose components are ID random variables, and you take a realization of this vector. And then by mu p here, you denote the expectation of the pth moment. Of course, yes, if the variable is bounded, then these moments exist. Then the following holds for all p larger or equal than 1. And what this thing says is that the probability of this ratio of this length of the vector to the expectation, right? This ratio, the probability that this ratio minus 1 in absolute value deviates by delta from 0 is less or equal than some exponential. And the important thing here is that this exponential is in dimension, unfortunately. So when the dimension grows high, even for, let's say, more complicated dependencies or like more complicated situation beyond the classical unit balls example, unfortunately, things concentrate. And this causes issues because if you work with general, let's say, high-dimensional data, and you have to, in the, and this is what I want to say now. So in the classical machine learning, we are forced to think, and in fact, we are forced to reject any assumption about what the distribution is. So you have to work with the worst cases. But here is an example for you for this worst case. So there is a large class of distributions for which distances concentrate. And then you don't need to actually look at this result. If you still apply the classical Hovding inequality, this is in a way is a restatement of a Hovding inequality. Then if you look at the ratio of the vectors in high dimension and the ratio of the LP norms of those vectors, and in fact, when I said LP norms, let's say quasi-norms, because I let P be a number which is just non-negative, right? Just, sorry, a positive number, not necessarily bigger than 1. So it's not a norm anymore, but a quasi-norm. So even for those P, you still have this, unfortunately, concentration, right? Now, the question is, can we do something? If you looked very carefully at this formula which I gave you, some of you are looking at this and some of you are not. Unfortunately, I can see from me standing here. So if you look at this formula, you say, wait a bit, there is something wrong here. What you say doesn't correlate with what you wrote. And in fact, this is true because if you look very carefully at this formula, if I let this P, let's say, small, if I let this P go to 0, then you may say, oh, wait a bit, if this P goes to 0, then this term goes to 1, and then 1 minus 1 gives me 0. So somehow I may have a mitigation here, right? So this term goes to 0, and then you multiply 0 by n, and then you have this exponent of 0, and you will be right thinking that way. But unfortunately, this is an upper bound, right? So an upper bound doesn't tell you what happens. So I can just put 1, and upper bound will hold true. But it gives you some hope that there could be something in, you know, controlling my concentration by P. So, and yeah. So why is this important, you may ask? I don't know whether you already met and whether you already seen such an object, let's say like a topological data analysis, or in fact any clustering method, or actually work with any clustering method in high dimension. But just to tell you why this is important, like on my previous slides, I said that distances, unfortunately, concentrate in high dimensions, and high dimension is wrong. But then I said, if I replace my norm as a measure of distance, and I go to quasi-norms, let's say, for things with p equals 0, or like close to 0, then I may get some advantage. Why I'm thinking about these advantages? The thinking about these advantages is that the concentration of distances is bad. So it's bad because all your clustering algorithms, k nearest neighbors, right? Those things go out of the window if distance is not informative anymore, right? Topological data analysis, when you try to build this barcode for your data, may also be sensitive to noise in the data because distance is concentrated and everything becomes close, right? So up until some distance, you see no neighbors in your graph, but then after a certain threshold, everybody is connected with everything, right? So it's not a very reliable measure, and that's why I hope that I make this point clear. Everything, so in high dimensions, this distance concentration is a problem. But then, in 2000, when was it? 2001, this author, Charu Agrawal, he said, ooh, there is something indeed when you go to quasi-norms. And that sparked significant and actually massive attention and massive hype in the literature, especially among people who worked with high-dimensional data. For example, people who work with omics, like with genes, expression of genes, when the number of attributes can be many thousands. For them, this is absolutely important. So the data there is not what you used to have. So you have a vector whose size is, let's say, 10,000 attributes, but the number of records that you have is only 100. So typical, dimensionality reduction techniques become somewhat useless there. Of course, people use them because they don't know, much what to do. But if you want to work with raw data and use whatever 1 and n classifier or something like this, because of the concentration, you are in trouble. So the problem is, can you replace it with something? And then Charu Agrawal said, wait a bit. If you take two random vectors from, let's say, an n cube, one is x and one is z, compute the distances, take the absolute value of this one and divide by a normalizing coefficient here. And then when you take n to the limit to infinity, the expectation that of this thing which you'll have is going to be equal to g, where g is a universal constant. But then there is this term here. And you'll see that this term is behaving in a very interesting way because it's sort of maximal when p is small. And in fact, when p is 0, you'll have it sort of in its maximum form. So Charu Agrawal then made the conclusion that, look, if you take p small, you can mitigate this concentration effect. And that received significant attention in the literature, and people started to doing that. And then guess what happened? It didn't help. So, and the question is why? Now, it didn't help, and one of the things that sort of here again, like is an indicator of what may go wrong in the analysis. Of course, his formula is right, but he looks at the expectation, right? So he talks about what happens if you keep doing this many times, but you cannot afford keeping doing this many times because you have one data point and you have another data point. He's talking about expectation, right? But you are interested in instantaneous values of the differences, right? So, and then, of course, we couldn't walk past this result, and we looked at it with ourselves, and in 2025, we published a paper where we showed that, unfortunately, for exactly those distributions that people believe are good, for example, uniform distribution in a cube, a product measure of identical distributions which are non-constant, unfortunately, you cannot get away You cannot get away from the concentration. So in high dimension, things will concentrate. So, in fact, what you can show is that the probability that the ratio of this sort of p quasi-norm, in fact, for all p bigger than 0, right? Provided that this term mu p exists, and remember what this mu p is. Mu p is the expectation, is essentially related to the existence of the pth moment, right? So if this thing exists, then the probability that you are going to be within, let's say, a delta shell, right? A delta shell of some ball, unfortunately, is close to 1 exponentially. And that's the settlement of the problem. But then you say, why are you talking about this? Because, well, it's a negative thing, so it's not very interesting. There is a twist in this story, right? When we got this result, we asked another question: are there distributions for which anti-concentration effect occurs? And this is where it gets very interesting. So at the same time, if your distribution is such, if your data is such, or let's say that it's generated from a distribution that has an atom at 0, what does it mean? An atom at 0 means that the probability of a random variable being equal to 0 is not 0, right? So if you have essentially data which can, with the property that 0 is an admittable, proper value whose of each attribute, and this probability is non-zero, then for these cases you have an opposite effect. So again, so if you have let's say classical Bernoulli trials with probability, let's say A, the value of this attribute is something, and with probability 1 minus A, the value is 0, or the other way around, with probability A, the value is 0, and with probability 1 minus A, the value is something which is not 0. For those data, anti-concentration occurs. And in fact, what you can actually say is that for any given, right, arbitrarily small delta, the probability that you will be within this delta, small delta shell around the surface of the ball is less or equal than delta. So what I'm trying to say is that you can actually pick p small enough so that you escape the concentration, right? And this is something important to bear in mind, and it's related to the fact that your distribution must have an atom at 0. So, and then here are some results, simulations which I created for you. So this is a classical, Bernoulli trial scenario where I produce data points, samples from a product distribution, and this is, the behavior of each individual attribute there. So with probability A, the value of x is 0, with probability 1 minus A, the value of x is 1, and I vary A, 1 quarter, 1/2, 3/4, etc. And then you see here, I plot the dimensions, and here I plot this, these deltas on the horizontal axis. And this is a coloring scheme enabling you to see, those probabilities, empirical probabilities. And you see that for A equals to 3/4, and in fact for all of them, around 0 here, right, you have nothing. So nothing concentrates. So just to be precise here. So I'm trying to right? I'm trying to measure the probability of concentrating around this delta shell, and delta, I think, delta is equal to 0.1 here, right? So, and when I increase the dimensionality, the probability of concentration near the shell is 0 for this case. But change this 0 to a small number, 0.01, and it all disappears. No, no anti-concentration effects. So, and this is perhaps the best illustration of what you need to be aware of when you work with high-dimensional data, especially with omics. So, and then there is another effect, which is a consequence of the two. So, suppose that you have a data, let's say, from a good distribution without atoms, right? What I'm trying to say is that in some small neighborhood of that distribution, there will be another distribution for which anti-concentration takes place. So, isn't it weird? So you can modify. Just let me rephrase it. So suppose that you have a data set, suppose that you have a distribution, and the data set is a sample from that distribution, and you know that for this distribution is good, for which distances, you know, should probably concentrate, so there are no, let's say it's a sample from an n cube, right? And what I'm saying is that in the vicinity of this distribution, in a small vicinity, there will be another distribution from which I can make a sample, and the sample from that distribution, samples from this distribution will show anti-concentration behavior. So just think about that. So why is it important? It is important in the following way. And this is a typical scenario, like I have two typical scenarios that people may consider important and maybe relevant and interesting. So in medical data analysis, or like in analysis of real data, there is one thing which is common. There are missing attributes, right? There are missing attributes in the data set. For example, well, suppose that I feel very bad, right? I call ambulance, and ambulance comes, brings me to emergency ward, and the doctors very, clearly see that I'm in a bad shape. There is no point measuring temperature because, he just or she just put her palm on my forehead, and they see that I have fever. So there is no point of measuring temperature, and then they proceed immediately to treatment. And here is an example of a missing attribute. There is no temperature record in my medical data for this particular event, right? So some analysis may be missing. Some other things may be missing. Age. So if something happened to me and a passerby phones an ambulance, and I'm rushed to again this emergency ward, and I'm getting treated, nobody's going to ask how old I am because I cannot tell, right? So missing attributes are common in medical data sets. Now, what people do when they work with data sets with missing attributes? One of the solutions that people use, they say, why don't we somehow replace this missing attribute with an empirical average? Why not? Well, possible. So that's what people do. Don't laugh, and please believe me that this is what's happening sometimes. And actually not sometimes, often. Let's replace them with some empirical average. But then what happens? We know that when you work with data, you have to normalize your data. You have to centralize and then normalize. You centralize your data, and guess what's going to happen? In those places where the attributes were missing, you have zeros, because you replace them with empirical average. So, and there you go, voila. Now you have a data set with some attributes taking zero values with a non-zero probability, and for this data set, anti-concentration happens. Even though for the original data, the concentration shouldn't be happening. Now, another example is when you try to perturb the data by randomly putting some noise into this data. This is another way where the zeros can occur and pop up by an accident. And in omics data, in genetic data, I think if I'm wrong, then I ask Professor Tyukin to shut me up and say you've run your, telling untruths. So many genes sometimes are encoded using the so-called dummy coding, right? Dummy coding is when you want to encode, let's say, a number for 1, 2, 3, 4. Instead of putting 1, 2, 3, and 4, you put 1 for, you encode 1 as 0, 0, 0, 0, right? 1 as 0, 0, 0, 1, 2 as 0, 0, 1, 0, 3, 1, 0, 0, etc. So it's called dummy coding. So you have a block of elements in your data which are encoded by dummy coding, and in these dummy coding encoding schemes, you have zeros. And for these data sets, you should expect anti-concentration. And this is, in fact, thinking. So if you work with these sort of data sets, then you know that, aha, if my data is dummy-coded, then I can take advantage of this p-norm, let's say quasi-norms, and setting p small enough to increase discriminating capability of my stuff. So it's not all negative, right? So, OK. So let me go next. And this is not related to us. So this is a very common, in a way, it's a common knowledge. When we work with high-dimensional data, we, of course, don't want to work with high-dimensional data for various reasons. Sometimes we want to reduce dimension. And when we reduce dimension, the first thing we do is we use principal component analysis, right? Like we compute covariance matrices, and then we compute eigenvalues and eigenvectors, and then project onto those eigenvectors whose eigenvalues are large enough, etc., etc. And here is the crux. Eigenvalues must be large enough, right? But the question is, how do we know that this eigenvalue is large enough? And what this Martian capacitor law says, and it's a theorem, it reveals you something else which may happen when you work with high-dimensional data and when you try to attack it, in a brute force way. So if you have, let's say, a random matrix whose entries are all identically, say, distributed, right, with zero mean and the variance equal to sigma square, and you take an empirical covariance matrix, and then what you do is then you introduce this empirical random measure which computes for a given interval how many essentially eigenvalues belong to that interval, right? And then on average, and then you take the you divide by d, right? So there are d eigenvalues, right? And d rows and n columns. Right. And the theorem says that if you let d and n go to infinity, but then fix the ratio constant, right? So if you fix the ratio being equal to lambda, then unfortunately your empirical measure will converge to some measure, but this measure will not be the one that you are expecting. It will be something resembling your typical diagonal situation where you want to have only one eigenvalue, right? Well, okay, many eigenvalues, but the value is going to be 1, right? Sigma square. You will have some deviation from that sigma square, and this deviation is determined exactly by the square root of lambda, and the square root of lambda is a thing where which controls the ratio of the number of rows to the number of columns. So if you want to visualize this, so how it looks for different lambdas, so for lambdas already modest, let's say 1, right? Or even for 0.6, and even for 0.3, you still have the spread of eigenvalues. And therefore, what I'm trying to say is that relying upon dimensionality reduction, blindly is probably not what you want to do. Now, so I said that there could be some issues which are related to various sort of flavors of robustness, and I gave you an example of this non-robustness in high dimension. But then the question is, suppose that we know that there could be issues. Can we verify robustness? And here comes a very interesting point, because what I'm going to tell you is that it's very hard. And in fact, it's nearly impossible. Now, so in order to do this, I would like to first introduce this notion of non-robustness and what it would mean. And I will start with the familiar notion that everybody knows, adversarial example. So yes, suppose that we have a classifier, which is a map from, let's say, Rm into the set of labels. And then we see that and say that for a given classification map F, an element X admits a delta adversarial example Y of X if the classifier returns a different value for X and Y of X, and the X and Y of X are, let's say, within delta, right? So that's the typical thing. And then I want to introduce another notion, which is called instability. The classification map F is unstable at X if for any arbitrarily small delta, there is some Y which is within delta of X, but for which the classifier returns a different value. So you see, instability is radically different from this adversarial business, because I'm saying that for any delta, right? So there, I'll say that there will exist, let's say, delta adversarial example is such a delta. And here I'm saying for any delta. So it's a very extreme bad property, right? Now, what I'm going to tell you next is that unfortunately, there is a family of paradoxical statements. All of them are true at the same time. So first, there exists a perfect and accurate generalizing AI model. Right? However, this model becomes unstable on a finite but large multi-set of points from the training validation data. And yet, accurate solutions exist which are stable. The problem is that you cannot get them. And then they become unstable, of course, for another distribution. So in order to set this, I'll let this sink into your heads, right? So, and this will have some interesting relation to high dimensionality. So there are problems for which you can find solutions with high accuracy. But those solutions which you found are unstable. And yet, within exactly the same class of models, there exists a good solution. But you cannot tell by just looking at accuracy whether you've got a stable or unstable solution. Right. And there is more to this. So why is it important? It's important because people realize that, stability is something that we need to look after. And there are some various legislative acts, let's say in Europe, in the United States, and then in Russia. I don't know whether you are looking for this space, but if you, relate your career and you connect your career path with artificial intelligence, then you probably should know that in Russia, Duma recently passed a law about AI systems. And I don't know, at the minute, our legislation is reasonably flexible, but nothing guarantees that sooner or later will be tied in the same way as European law, which says that models have to be robust, reliable, explainable, etc. So all these things which I'm talking about, they are important. Now, to set, to give you something formal, so what I want to do, I want to consider a case and I want to exemplify this case where these three paradoxical things occur at the same time. So let's consider classical scenario when we have a feed-forward neural net with some ReLU, units, right? So this is what everybody knows, and I want to just set up the notation. So I have these affine maps here, and I have the output, which is let's say a 0, 1 threshold function, and then I have these activation functions here, and the dimension of this input is d, and the number of the layers is L. Okay, so what I'm going to do, I think I can skip this one because this is what I already said. And I assume that I have access to samples, training samples and validation samples, right? And they are ID samples, independent samples from some distribution, right? And the cardinality of this training and validation is M, right? And because I want to talk about stability, I want to constrain myself so that I cannot cheat, right? So how do I constrain myself so that I cannot cheat? I should prevent my data points concentrating and coming close together, arbitrarily close together. And this is what I'm writing here on the slide. I'm saying that if the label of the point is different, right, and they are sampled from my distributions, the delta, then they have to be at least delta apart, right? That's what I'm saying. So I'm not enabling cheating for me, right? Although I will cheat. Unfortunately, that's how you work. So, but I'm setting up the thing that the cheating is not permitted, okay? And then you have the loss function, which is a classical one, which is 0 only when the labels coincide, and which is non-zero when the labels are different. Okay. So, and here is the result. The result is this. So you fix a neural network. So you consider a class of neural network whose input dimension is d, and the second layer is bigger than 4, right? And d is bigger than or equal than to 2. Right, you have L layers, whatever, and as n, you pick, the minimum of n over n and 1 over 2 in d. So the minimum number of this one can be 2. So, and then I pick an epsilon from the interval, which I'm specifying, like let's say some interval, and I fix the delta, right? So the delta controls distance to my points. I fix it, so I'm not letting points to come closer, right? Closer than delta. Now, then there is an uncountably large family of distributions, I call them d delta, such that for any training and validation data drawn independently from this distribution, with probability 1, the following happens. There exists a good solution. This good solution gives you 0 loss on your training, 0 loss on the validation, and 0 loss for any future samples. Good, right? Yet, for any q, let's say q is equal to 1,4. When I set q equals to 1,4, I'm saying that a quarter of my data will be affected by the property that I'm going to talk about next, right? So with probability equal to 1 minus exponential q squared m, and if m is large, the cardinality of training and validation set is large, that means that this is close to 1. There is a subset of cardinality at least 1/2 minus q. So I said, let's pick q equal to 1/4. So there is a subset whose cardinality is at least 1/4 of your training and validation data set, right? On which the network is unstable. Unstable in the sense that for any point from this data set and any arbitrarily small neighborhood of that point, there will exist another point within that neighborhood that swaps the decision. So think about it. For a quarter of your data, you will have this bad behavior. And if you think, well, but existence doesn't mean much, what I'm trying to say next, you can pick this swapping point at random. And this is what the next result says. Yeah. So yes, there is a perfect solution, but this solution becomes unstable on a reasonably large set of data points because the classifier actually changes its output. But then what I'm saying is that you can pick it at random, and with high probability 1 minus 2 to minus n, and if n is 10, let's say no, n is 4. 1 minus 2 to minus 4, which is a reasonably close number to 1, right? Your random draw in that small neighborhood produces a swap of the label. And in fact, it's not only this. Once you produce this perturbation which swaps one label, with high probability, you swap that same perturbation has a negative impact on other data points. Right. And this is where it gets interesting, even more interesting. You may say, look, but this is a sort of somehow a ridiculous situation. You cooked some counterexample. Now, if you give me at the same time, there is a good solution which generalizes and which also is robust. And then this gives us some hope that, in fact, we can get something using some gradient approach, some regularization, etc. But then what I'm trying to say next, if you give me an arbitrary small number, arbitrary small, then I'm going to give you a pair of networks whose characterization in the parameter space will be this. So the weights will be within this delta, whatever, small number neighborhood that you gave me. But one of them, so in parameter space, they will be almost indistinguishable. But one of them will be stable, another will be unstable. Right? And also at the same time, they can be arbitrarily far apart. So if you give me a large number, I can give you a pair of networks. One of them will be stable, one of them will be unstable, and in the weight space, they will be far apart. Okay? Now, however, for the above network, which is robust, there will be another family or uncountably large family of distributions for which the network actually loses robustness. And there are some other consequences which are related to dark data. And what I'm trying to say, if you verified your thing for these distributions on some fixed number of points, and you are sure that the behavior is robust, with some probability, this probability, you see, if n is large, then this is reasonably close to 1, right? There will be some unstable point further down the road. Okay, so do you think this is somehow artificial? I bet most of you are saying, well, these people who do this analysis, they create some counterexamples, and these counterexamples are specifically constructed to amuse us. They're alto examples. But here is the interesting thing. I have to admit that this is I used my friend Claude to help me with this experiment. I asked Claude, dear Claude, can you please do this for me? Take classical data sets, MNIST, Fashion MNIST, CIFAR 10, right? Take several networks, and please do these experiments. Pick one class at random, and the rest of the classes will be another class. Train the model and compute the following thing. Compute the median distance, right, to the decision boundary, right? The median distance to the decision boundary for each data point, and then compute the minimum distance minimal distance between points belonging to different classes. And give me these numbers. Because you see, I'm trying to measure the following. There is a distance between classes, right? And then there will be distance to the decision boundary. And that's what I want to measure. Because my thing says that, well, there are distributions, blah, 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 which are unstable, and they can be very exotic. So MNIST, function MNIST, whatever, they're not exotic distributions, they are standard benchmarks. Now, so, and I took shallow neural net, I took a medium CNN, right, and then a deeper, like 2 layers, 4, 6. And here are my results. So what I'm showing here is the ratio, I'm showing you this number, right? The ratio of the median distance to the decision boundary, not the minimal, the median, and to the minimum between classes. And the ratio is very funny. For MNIST, the maximal is 0.26. So the distance to the decision boundary is 4 times smaller than the minimal distance between classes. And this is where it gets interesting. You see? Interesting. It's like, it's like innovation. Thank you very much. Yeah. So, and this is where it gets interesting. If you look at deep neural nets and shallow and medium neural nets and CIFAR data set, which is more higher dimensional than MNIST and function MNIST, then the ratio is 25. The distance to the decision boundary to the distance, between classes is 25 times smaller. So what I'm saying is not just some abstraction. These things happen and they occur. And again, so a signature of this is high dimensionality. I have some explanations for this phenomena, if you may ask, but not for this talk. But when the dimensionality increases, you have this interesting phenomenon. When somehow this instability gets woven in. Look, there is no reason why a network, why a solution has to be that way. I didn't do anything. I just ran, gradient, typical stochastic gradient descent, and this is what I've got. Okay? Now, so, and again, you may say, look, I said uncountably many distributions exist, etc., etc. And you can say, well, but we know that this doesn't mean much because it doesn't tell you whether these distributions are numerous or not. But the interesting thing, which we have proven just recently, and I'm not going to go into much detail, I just want to declare this. For if I relax the problem just a little bit, instead of asking for stability, I'll ask for some non-robustness up to epsilon or delta. So for those in this setting, if I relax the problem a little bit, for every distribution, which are uncountably many, there will be a small neighborhood of other distributions for which the same unfortunate property will hold true. There will be good solutions, they will be not robust, but there will be good solutions which are robust, but you cannot tell whether you got a robust solution, a good one, because you have to do something. And unfortunately for these examples also, telling robustness from non-robustness essentially requires checking every single point. And when the dimensionality grows, the number of your tests must be exponentially large. Now, reflections. So I hope that it puzzled you sufficiently to think about this property. So why getting a solution of high accuracy is easier than actually testing and checking its robustness? And it's very, very easy because in some instance, accuracy and generalization depends on the number of dichotomies in the binary classification which the classifier is able to produce. And typically, when the problem is learnable by our model, then this number of dichotomies is a polynomial of the size of the data. However, for each such dichotomy, there could be a continuum of different functions implementing this dichotomy. So for each dichotomy which you have polynomially many, there could be a continuum of realizations of this dichotomy in your model. And this is where the tension lives. If you want to verify verify stability and robustness, you have to be searching in the class which is much larger than a polynomial, right? So, and that's where this tension between the classical generalization bounds and the verification of accuracy, so stability and robustness, right? Now, you may also say, look, but there are tools. There are tools that enable us to, verify and ensure robustness. For example, randomized smoothing. And here is an example of those tools. Now, what I have to tell you up front, for the setup which I have in this theorem, randomized smoothing does not apply. Because it stabilizes your solution. There is nothing wrong about it. But this solution which it stabilizes is the worst solution that you can have. So its accuracy is the worst possible. It's going to be a stable but bad solution. Okay? So randomized smoothing doesn't help in these instances. So, okay. So now I'm coming to the next one. So you see, first I said about my first topic was, can something go wrong in high dimension? And I told you yes. The second was, well, okay, if something can go wrong and if things can become unstable, can we verify it? I said, no, you cannot. And then adversarial things. Adversarial things is something that, somehow captures the situation where things normally go well, but small change swaps, your model's output. So now I want to increase my demand, and my demand is to answer the question whether these things are typical. Can you expect it? And in fact, the answer would be yes, they're typical, and I'm going to give you a series of examples, formal statements, which will somehow follow up from the example which I just showed you in this sort of classification with MNIST, function MNIST, and CFAR, this ratio between the decision boundary and the distance between classes, right? So the fact that the distance to decision boundary is small is not unusual. Now, what I'm going to tell you that there are tasks in which, with high probability, a randomly sampled point is susceptible to adversarial attacks. Adversarial attacks can be universal and transferable, in fact, and they could be remarkably easy to compute. And yet, with high probability, random perturbations do not lead to any issues whatsoever. And this is the interesting thing about high dimension. So, and I will start exactly with this example. And this is what one of my postdocs did when we worked on this, because I knew that it's going to happen. But you see, you guys, you are young. You don't believe and you trust your supervisors. And of course, you want to try. And he tried. There we go. So you have a typical image, a cat, right, from a CFAR, from this famous CFAR data set. And, you performed some adversarial attack on this cat. And this is the attacked image. Some resembles that it's a cat. And this image here is another image to which some perturbation was applied. But the perturbation was a random perturbation added to this image, right? And the classifier believes that this is a cat. This is not a cat. a cut and not a cut, right? So what's wrong? So when I perturb my data at random, as a human, I cannot see much. But the machine sees a cut here. When I don't perturb much that image, the machine doesn't see a cut, but I see a cut. And in fact, you can move on, and if you wish, you can make this experiment yourself. And this is what I'm planning to show you now. So you can, in fact, build those plots where you have, on one axis, you plot the size of your adversarial attack, and on the vertical axis, you plot the proportion of data points for which the flipping occurred for that level of your attack, right? And you see a very nice picture that after some size of your adversarial attack, mostly all of the data points flip the labels. But if you apply random attacks, and here on the horizontal axis, I plot the ratio of the size of the random perturbation to the size of my adversarial attack. Then when the size of my random perturbation is 5 times the size of adversarial attack, but I'm doing this at random, nothing happens. My model is robust. Right? And when it's 10 times, only then I get to the level of maybe 30%. So, and the model still sees the original data. I don't know how to exploit it. Maybe it's a new, cryptography scheme or whatever, something that may enable you to encode stuff. I didn't think about this, but interesting. So the question is why this happens. And in order to answer why this happens, we looked, of course, at a scenario. Why don't we look at this mathematically? And so we said, look, okay, so here is class 1, here is class 2, here is some decision boundary, but it's too difficult to analyze. Why don't we just take this little ball and think of those, think of the data within, let's say, this ball. And this is what I tried to depict here. Here is class 1, class 2, still difficult to analyze. Well, let's say that we looked at these cases where you have one class is associated with the ball D1, another class is associated with the ball D0, and between those balls you draw a line or like a hyperplane, which is the separating boundary between those two balls. And that's the object of interest. This is it's a spherical horse in a vacuum, right? So that's what we do, right? So we don't want to work with real life problems. We work normally with spherical horse in the vacuum, although some of us actually do work with real life problems. Now, so this is the setup. So suppose I have my class 1 associated with this ball, class 2 associated with that ball. The balls are separated by 2 epsilon, right, away. So the centers of them are 2 epsilon away, and epsilon is a distance to the decision boundary here. And I think I convinced you before already that this distance to decision boundaries can be small, right, from my previous experiments. Now, and my decision rule is very simple. If x1, which is a coordinate of the first coordinate of my sample, is smaller than 0, then it's class 0. And if it's larger or equal to 0, then it's class 1. Very simple decision rule. So now, what can I say about this setup? For this setup, you can draw the following conclusion. In a way, you can call it a blessing of dimensionality. You see, for any epsilon, you can fix this epsilon and make it arbitrarily small. So for any epsilon from 0 to 1, the probability that this stuff gives you a correct solution, right, very simple solution. Maybe that's an explanation why we have this problem when our stochastic gradient descent finds something that performs well, but it's not robust, because it's easy to find these solutions, right? So the probability that you have a good, correct solution is close to 1 exponentially in dimension. So n is a dimension, 1 minus epsilon squared is, of course, less than 1. And when you raise this to, let's say, if you think about dimension of an image, so like your typical MNIST image is about 900 something, right? So when you raise a small number to 900 over 2, you have something close to 0, and the probability of getting a correct solution is close to 1, right? First result, things are good. Now, unfortunately, for any epsilon again, and any delta, which is your adversarial sort of radius, right? Radius of the attack. The probability that this randomly sampled point, so you are sampling at random, you are not picking the worst, you are sampling things at random. The probability that a randomly sampled point is susceptible to an adversarial attack with Euclidean norm delta grows exponentially to 1 with dimension. So again, it's largely almost always because of this exponential concentration in the volume. But this is very interesting because typically, and that's exactly what we've seen, and I'll show you later in other empirical proofs for this one. So you build a model, you don't regularize it, you are happy with this solution, pick a point at random, and then it's typically susceptible to adversarial attacks. Now, and here comes the interesting twist and the punchline. So the models are susceptible to adversarial attack, but when I add the random perturbations, these models are remarkably stable. So if I produce, right, let me read it. So for any epsilon, right, epsilon is a distance to your decision boundary, and any delta from epsilon to 1, the probability that a randomly selected perturbation with Euclidean norm delta causes a randomly sampled data point to be misclassified, right, converge to 0 with dimension m. So I may pick delta as close to 1 as I wish, and 1, remember, in this scenario, is the size of my universe in a way, right? Because the data are all within, say, 1 balls of my, right, within balls whose size is 1. So I'm perturbing my data as much as I can, right? But regardless of this, if I do it at random, the probability that I get an occasional flip goes to 0, robustness. Now, there is something else. The universality I told you. So the question which you may ask is this. Suppose that I randomly drew a point. I computed an adversarial perturbation for that point. What are the chances that the same adversarial perturbation will be adversarial for another random point which is sampled independently? And the chances are close to 1. So, and this is what theorem 5 says. So the chances that for randomly sampled point, when I compute an adversarial perturbation, meaning that I destabilize this point with this perturbation, what I'm saying is that all perturbations which destabilize this random point will also destabilize another random point with probability close to 1 when the dimension grows. And this is not all. These destabilizing perturbations are easily computable. So they are along the gradient lines. And this is what makes the whole thing a little bit funny. So I can easily compute those things, but when I do things at random, I retain robustness, right? And and this one. And this was a very interesting thing because it reveals you that somehow it's not only the concentration in dimension, but it's the gap between the two classes, which is important for all these things to coexist. So let me read this statement first. So suppose that you have these classes now, not like balls, but let's say half balls, and I put some epsilon between them. And what if I let the epsilon be 0? There is no margin between classes whatsoever, nothing. We know that everything concentrates. For this class, things should concentrate around this bit, things should concentrate around that bit, and the machinery is such that you sort of like your random perturbation doesn't move too far from this to this one. But if you set the margin to 0, random perturbations start flipping the labels. So all this sort of stealthiness disappears, and you can visibly see the problem. So this is why I called it no place to hide when margins are 0. So when the margins are 0, concentration is not as bad as you think. So you immediately see the problem, right? So when you don't see the problem is when you have a non-zero margin. So think about it. When your solution is somewhat stable, right? Yeah, so when your solution is somewhat stable, you have this problem when adversarial attacks exist, but you cannot spot them by randomly perturbing your data. You see, there is a bit of, stealthiness occurring here. Now, the thing is, and that's what I made this remark. That's why I made this remark. Are stable models good? In some sense, yes, they are good, but there is another, negativity and another danger about the stable systems that they're good, but in a way that they are stable to random perturbations, but there is nothing that sort of tells you about their susceptibility to adversarial attacks unless you verify every single point, right? So, and then some examples, of course, we've done a model and a CFAR dataset, and I'm going to show just very quickly go through those slides. So accuracies, if I take class 0 as a class 1 and class 1 as class 2, so those pairwise accuracies, you see they're pretty high. And then the interesting thing is that susceptibility to adversarial attacks, unfortunately, they're also high. Exactly as the theorem predicts, they will be susceptible, those things, to adversarial attacks. And then if you look at the sizes of perturbations, let's say these are the perturbations corresponding to adversarial attacks, and these are the perturbations corresponding to random attacks or random data perturbations that result in the swapped labels. You see how large discrepancies are between those two. So the random perturbations must be much, much larger to result in a label swap than the adversarial ones. So, and I think I'll skip this slide because I don't have the time. So now the picture is bleak, right? You can see that there is no way to go. Somehow, and this is me, in fact. So high dimensionality may result in distance concentrations. I cannot go there, right? So distance-based methods fail. Create sensitivity to zeros popping up in data processing pipelines. I have to be now very careful because, as I told you, there is a massive difference in asymptotic behavior and, in fact, non-asymptotic behavior between those distributions which have atoms at 0 and those that don't. Makes verification of robustness hard and facilitates stealthiness of adversarial attacks and their immunity to data augmentation. So somehow you have this impasse. is there any good in high dimension? And this is what I'm going to tell you. Yeah, this is my picture which I tried to visualize. Somehow you build the barriers, you certify the model, blah, 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 blah. But then unverifiable behavior, because of dimensionality, of course, breaks in, and then something needs to be done. And the thing is, a priori certification is hard. So, and I think it's fundamental, because when you're trying to certify something within the concept of, within the classical framework of machine learning, where we refuse accessibility and availability of any knowledge whatsoever about the data distribution, we consciously try to refuse this. But then, at the same time, we want to produce an a priori certification, and somehow it's no surprises a priori certifications are hard because we know nothing. So what can be done? And one of the ways is to actually produce a posterior certification. Suppose that you have your data, and suppose that you have some errors, and what you want to do, you want to wait maybe, because you don't have any other way until these errors occur, and you want to learn from those errors in runtime. Yeah, that option is feasible. But here comes the problem. If you do it, classically, so let's say you have the data, you accumulated some errors, and then you want to build another model. The problem is, because the thing is not very controlled, and it may be expensive, but in a way, the outcome is going to be a random number anyways, and there could be other errors which may occur. So, and I'm going to tell you about this ideal scenario. The ideal scenario is this. I have my good data, which is shown here as these green dots, green disks on the slide, and I have a bad data. The bad data is Y. What I want to do, I want to build a magical device which takes this bad data, Y, and for this bad data alone, without looking at the good data, because this device may not know the good data, computes a separating hyperplane for that bad data, so that the bad data point is on one side and the good data point is on the other side. Yes. I will let this thing to sink in your heads. So typically when we solve this problem of separation, we know the good points, we know the bad points, and our solution depends on both, on the good and the bad points. What I'm trying to do now, I don't want to know anything about the good points. I want to know the bad point. And knowing only the bad point, I want to separate this bad point from the rest by building some linear plane whose parameters will depend, of course, only on the good points and not on the bad points. Do you think it's possible? And an honest answer would be, I don't know. Well, yeah, well, of course. And in fact, I want to even say you that in some instances it's not even possible, because this is an example of me drawing some random points from a equidistribution in a square. These are blue ones, and the red one is, let's say, the point I want to separate. No way I can do this. No way. It's not possible in 2 dimensions. Dimension. Now I said the key word dimension. You can say, yes, dimension. True. So when n is reasonably large, in a typical position, let's say n plus 1 points will form a simplex in n-dimensional space. And every vertex of that simplex is linearly separable from the rest. I'm not going to tell you how, but at least we know that it's linearly separable. But here comes the problem. So if my dimension, let's say, is 1,000, this applies to data sets up to 1,001 points. What if my data set is 10,000 points, or maybe 100,000 points. Can I do the same? Unfortunately, in this case, Radon theorem says that you cannot guarantee that you can do, because for dimensions, for dimension n, the sets comprising of n plus 2 points will contain partitions whose convex hulls intersect, meaning that those partitions are not linearly separable. So is it the end of the story? No, it's not the end of the story. And now I want to quickly, very quickly, introduce this concept of stochastic separation. Now, so suppose that I have a point x, and suppose that I have a set y. I'm not thinking and talking about distributions, just a set x and set y. And I said that a point x is separable, Fisher separable from the set y with the threshold alpha if this property holds true. So, and in fact, if you do the math, you'll see that the separating hyperplane is exactly this one. So you put, instead of the dot, you put y. So if you put the y, then you'll have xy, and I'm interested in this set L of y equals 0, right? So, if my alpha xx equals to is bigger than xy, then when I put y here, I'll have that xy will be less than alpha x squared here, right? So, and that means that this L of y will be less than 0. But if I plug x here, L of x will be bigger than 0. So therefore, so when at least alpha is from 0 to 1, right? So this is a valid separation hyperplane, and I call this separation Fisher separable. And the interesting thing here, this hyperplane depends exactly on the point x, and it doesn't depend on the points y from the set, right? So that's how we define it. So geometrically, this means that the following. So this inequality means that x is not inside the ball, which is formed by me drawing a line from 0 to y over alpha, and basically dividing this line into 2 and drawing a disk around that point which I got, right? So, and it's very easy to see why this is happening, because if you define this ball as I just drew, and you expand those norms, you'll see that certain things will cancel out, and you'll see that this inequality is an equivalent, it can be equivalently restated as a property that x does not belong to this ball. It will be important later. Now, and here comes the punching line. So the punchline is this. Suppose that you give me any vectors. They don't have to be even drawn from some distribution. And in fact, you don't give me those vectors. You keep it to yourself. You don't tell me these vectors. Actually, we could play this game if I would have the time. I would ask you to give me some vectors of your likings, right? And then what I want to do, I will draw a random point, but now from a distribution which satisfies this property. So the density of this distribution should be somehow bounded from above. So if you think that by this number, so pick an r from 0 to 2, and bound this density. So if you have an equidistribution in a ball, this condition will hold true. So I draw a point from an equidistribution in a ball. Now, once I've done this, I claim that x, the point which I drew at random, will be Fisher separable from the entire set y, which I don't know. I have no access to this set with this probability. And now you see that this probability is going to be close to 1 exponentially in dimension. And this is one of the blessings of dimensionality when it comes to posterior certification of robustness and accuracy in your in your AI models. Now, right? So you created those set of points. Why? You don't tell me anything about those vectors. I draw a number x, a point x from this equidistribution in a ball, and I'm telling you that with high probability my x is separated from yours, even though I don't know anything about your points. And the thing is remarkable because that's the thing which somehow works. So I'll share the slides. I don't have the time. I don't have left much time to actually continue with this. I probably will focus on this one. So you may say, look, and here is a geometric explanation of what's happening. So if you take some random points in two-dimensional ball, you'll see some messy picture, right? And in this messy picture, what you'll see is that some points are extreme points and some points are not extreme points. But if you increase the dimension, one of the consequences will be that all the points are going to be extreme points. But then you can say, isn't it not surprising? Isn't because we have this shell concentration? And I have to say that indeed the shell concentration takes place in high dimension, but the problem is shell concentration doesn't tell you anything about the structure of those points within this epsilon shell. So what I'm saying is that the property that I'm relying upon, and you can actually get it proved, is that every single point with high probability will be an extreme point. So basically, if you build a complex, if you build a polyhedron out of your random sample, it will be a complex polyhedron, which is a nice thing, nice property. Some people looked at it in the past, of course. There is a Barony and Freddy in 1988. They looked at this and proved it for uniform distribution in balls, and then Donoghue and Tanner for Gaussians, and we proved it basically in general case that this is exactly what's going to happen. So I'm skipping this argument. It's for you. I presented it here, but maybe it's not important. Now, if you want to know a little bit more about this magical effect, you see the effect is very simple. In high dimension, you draw a random point. You forget about the other points. You don't have to learn about nothing about them. You don't have to know about them. So, and this random point would be Fisher separable from the rest. And you have a closed form solution which separates them. And in fact, you can do more, not only for these distributions, which I said, like with compact support, or supported in the convex sets. You can have distributions without compact support, let's say any log concave distribution, which you centralize and normalize, could also have this property, but for this, the universal solution is slightly different. And in fact, there is a universal formula that gives you this closed form solution for distributions within the class of log concave, which are centered and normalized. Here is a paper which we wrote with my co-authors. Is a very introductory and nice work where we try to trace the problem back to some maybe 200 years ago, and related to some famous mathematical conjectures, which been only it's a Bourgain conjecture, which been proven in 2025. So it's a nice mathematical game in its own right. Now, does it work? And here is my first example, which somehow we've got some time ago, but I really liked it, and I'll show you. So at the time, we've been working on a problem where our partner was building a model, and the model was getting too many false positives. And the question was, can we actually fix those false positives on the go? And we used that theory to do that. So we took a classical VGG model, so it's an object detection case, and then worked in this space with these embeddings and used them as sort of feature vectors. And every false positive was then introduced in that model and corrected in exactly the way I said by these Fisher hyperplanes. And here is the result. I probably will show you this video if it plays. So at the top you see the regional model's performance, and the yellow rectangles show false positives, and those are the errors we want to filter out in runtime, right? Without impacting the rest. And this is exactly what's happening. So you filter them in runtime, and the performance does not change exactly because of this property. As I said, like, you keep your y vectors, whatever vectors they are, you keep it. You draw them, you created them. I don't want to know them. When I have an error, I separate it by this Fisher hyperplane, and I guarantee with high probability nothing's going to happen to your model performance. And that's precisely what's happening. So there are no yellow boxes anymore here, and the model's performance is rather comparable. So like, you don't visually at least see any degradation. So there are other examples where you can actually use the same technology, and one is the edits of LLMs. So when you work with LLMs, and LLMs produce either a hallucination, and I think Professor Zaitsev will tell you more about those hallucinations at some point, and about the methods of detecting hallucinations. But suppose that you detected hallucination. Can you remove it? Please, now. Don't do hallucinating output for me. So the answer is, well, that way you can. At least we've shown the feasibility, but there is some work that needs to be done here. So, and then, can you do more? And in fact, you can, exactly in the same way you can use it for security. You can lock a model so that you can log the functionality of that model, so that without the presence of a watermark, a model will do nothing. And it's very good, because that's the way you find the distillations. And if you have an asset that you don't want to share, and you want to only share it with to people you trust, to whom you actually produce a watermark, and then you can use exactly the same technology. So, and I think it works with the generation, the generative AI too. You can log generations and not only classifications, and the results we presented in last year's ICCV. So, and I think without any further ado, I approached the end of my talk today. So, the first message is simple. So modern AI tasks, models, and technologies unfortunately become increasingly high dimension. And this high dimensionality, I hope I convinced you, is something that you don't dismiss. You actually respect it, right? So high dimension requires a very delicate balancing and attention. And there are certain limitations which come with it, and we need to be aware of those. Now, there are some benefits of high dimension too, because, unfortunately, the universe we live in is not malicious, right? So it's not always bad. There are some good things too. For example, you can, take advantage of it, and you can use it for alignment. You can use it for learning, actually very cheap learning, and you can use it for, increasing security, etc. But there are some open problems, and the area is live and active, and I invite everybody in this room to join us and contribute to this nice and interesting topic of high dimensionality, robustness, and stability. Thank you very much.
Hello. Yeah. Thank you so much for so interesting talk. Probably could you explain in simple words how the following statements are connected? That on one hand, in the vicinity of the bad distribution, so you statement, we have in the vicinity of the good distribution, we have a bad distribution. Then we have a fundamental result of SMILE that structurally stable systems are not dense. Yes. We have his horseshoe systems, for example, yes, where in any point of the phase place plane, we could have a bifurcation, so it's in principle a system with a huge informational capacity. And in the same time, human brain, for example, are probably using something to be very effective and probably even ghost attractors. So how all these statements joined each other
Okay,
together?
so thank you very much for the question. So so the question relates to this one. So for Smale, right? For this Smale's nightmare, what he says is there are bad systems, right? Like this, bad systems, and then there are neighborhoods. There is a neighborhood of systems around this bad system, and all systems in this neighborhood is bad. So, you know, the good systems are here, and unfortunately, you cannot approximate a bad system by a good system. So you have to live with bad systems, right? Structurally unstable ones. So in exactly the same way, the theorem which I presented in exactly the same way. So what I'm saying is this: there are systems, or there are distributions, and there are uncountably many distributions which are bad. But uncountably many is a very vague thing. Is it really bad? Like, are they really numerous? Can I assign a measure 0 to these uncountably many distributions? And what I'm saying is this: around which distribution which is bad, there are neighborhoods of nearly equally bad distributions. So the claim is topologically significant. You have to assign a measure 0 to all those neighborhoods if you wish to neglect them. Mm-hmm. So that's exactly the same. So if the task is bad, you cannot approximate it by a good task, right? So you have to live with learning and knowing that there are bad tasks.
I guess I'm the next one to question. You were, first of all, thank you for the talk, an interesting and charismatic one. You were talking about the limitations of metric methods, including the examples of persistent homology building. And you just told that the measure concentrates all the dynamic range of different available distances between various points is small, so most of them are more or less equal. But of course, that's just a heuristic, and that does not necessarily mean that these methods would work bad, because maybe we should just use the scale of distances in which it will be okay. Are there any methods that, maybe bounds that show that if it is okay or not in the dimensions where the topological data analysis is computationally feasible? Thank you.
Thank you very much. A brilliant question, because the question relates mathematics and reality, right? So there is one thing which is mathematically correct, which could be a correct theorem, right? A correct statement. So the thing which I said before related to statements like this, right? So for a large class of distributions, unfortunately, you have this problem when the probability of landing within a delta shell of some ball is, close to 1. But here is an interesting thing here. This guy, f of delta. Yes, it does not depend on dimension, but it may be small. So what you are saying is, well, we know that topological data analysis works, and we know that it works well, and it gives us a good invariance of the data. I do not deny that this is true. Yet, there is a limit, and that limit when n gets very large. So when n gets very large, you know, tens of thousands, hundreds of thousands, we have to be a little bit more careful when we do, because at those limits, I'm not saying that the method's not going to work. I'm saying that it will become sensitive to your samples, right? So because we are talking about the probability of landing within, so and that probability will depend, of course, on your sample, right?
I mean, it would depend on the exact points or their
Exact
distances.
points, yes, exactly. So the concentration of distances will be there, and the results may become sensitive to your data. That's what I'm saying.
Yeah, doesn't it work the way that the points are not stable themselves, but the distances in this narrow range are
Yes.
still stable?
So I think it's so yeah, the distances will be stable because they will concentrate, right?
Yeah, I mean, they're ordering a ranking of distances. I mean that the significant parts.
That you cannot guarantee because it becomes a probability thing, right? So exactly, because when you're ordering, that's what I meant. So for some dimensions, this ordering may start behaving in a somewhat unreliable way. But I'm not saying that you'll face it necessarily at the dimension 1,000, etc. It largely depends on the data. And for some data for which TDAs is applied, for example, for this genomic, etc., you have naturally the other extreme. So you have anti-concentration behavior, so your ordering probably should be fine. Yeah?
Yeah, and probably topological data analysis for even second-order homologies just is computationally infeasible for very high dimensions. So
yeah, that's true. Yes.
Okay. Thank you.
Yeah, yes. And I asked those questions to people who actually do TDA in London and in Oxford. Elika Ullman, I asked her, and no, not her. A person was from her lab was making a lecture at some point, maybe 3 to 2 years ago, and I asked this explicitly. You are using this, you're applying the method to biological data, and this data is typically high dimensional, but there is this sort of potential, you know, noise in the ordering when the dimension gets high, and the response was yes. We certainly, yes, we know.
Thank you for the lecture. It was interesting. I'm an applied scientist, and early in your lecture was discussing a case when we have data points close to each other, which are similar to each other. And do you have some practical advices how we can work with such data, how we can identify such problems in highly dimensional big data sets and mitigate the effect of this? Thanks.
Thank you. Difficult. So the thing is, when you work with high dimensional data, normally the number of samples is not very large, so your statistics is not informative too. So what I'm trying to say is that maybe you need to use methods which do not rely upon distances. So use ensembling if the task is classification. So start with the weak classifiers. So do not try to reduce, because I said later in my lecture that if you try to reduce dimension, then you'll have another set of problems, right? So maybe a natural way is to work with weak classifiers and do ensembles, etc. Yeah.
In my domain is chemistry, and often we face with a problem of representation when two molecules could have different molecules with different activity could have identical representation. Do you know something how we can work with this?
Oh, well, not from the top of my head, but I would be very interested to look at this problem, because you'll probably need to see and wait until Professor Zaikin's lecture today, and we are working on a set of methods that may be of interest to you. So let's talk about that. Thank you.
Thank you.
Yeah.